Right now, 48 light-years from where you sit, there might be an ocean. Not just any ocean, an alien ocean, under an alien sky, on a world that orbits a star smaller and dimmer than our Sun. Scientists using the James Webb Space Telescope have detected hints of something extraordinary there. Hints of an atmosphere that could shield liquid water. Hints that this distant world, called LHS 1140b, might be the closest thing we have ever found to a second Earth. This is not science fiction. This is happening now, and it changes everything about how we think of our place in the universe. For thousands of years, humans have looked up at the night sky and wondered if we are alone. Ancient philosophers speculated about infinite worlds spinning through the void. But until 30 years ago, we had no proof that planets even existed beyond our solar system. Today, we know of more than 5,000 exoplanets, worlds orbiting distant stars, and the James Webb Space Telescope is revealing their secrets in ways we never imagined possible. We are living through the greatest era of cosmic discovery in human history, and JWST is our guide through this new frontier. The search for a second Earth is not just about finding another planet. It is about answering the most profound question ever asked. Are we alone? Is life a cosmic accident that happened once here on Earth, or is the universe teeming with living worlds? Every observation JWST makes brings us closer to an answer. The telescope has found ocean worlds and lava worlds and planets with atmospheres that defy explanation. It has discovered chemical signatures that might indicate life, though scientists remain cautiously skeptical. It has shown us planets where diamond rain falls from carbon clouds, and worlds tidally locked to their stars with one side forever day and one side forever night. JWST launched on December 25, 2021, from French Guiana aboard an Ariane 5 rocket. The telescope is the most powerful ever built, with a mirror 6.5 meters across, nearly 3 times the diameter of the Hubble Space Telescope. It orbits the Sun at a point called Lagrange 2, about 1 million miles from Earth, where it remains in sync with our planet's orbit. The telescope's massive sunshield, the size of a tennis court, keeps its instruments at temperatures near absolute zero, cold enough to detect the faint infrared light from distant worlds. This infrared vision is crucial because many of the molecules we seek, like water vapor, carbon dioxide, and methane, reveal themselves through their infrared signatures. The telescope cost $10 billion and took 20 years to build. Thousands of scientists and engineers from NASA, the European Space Agency, and the Canadian Space Agency worked on the project. The mirror consists of 18 hexagonal segments coated with gold, each precisely positioned to act as one enormous light collector. 4 main instruments analyze the light the mirror captures. NIRCam. The near-infrared camera takes images and spectra of distant objects. NIRSpec, the near-infrared spectrograph, splits light into its component wavelengths to identify chemical compositions. MIRI, the mid-infrared instrument, observes longer wavelength infrared light. And NIRIS, the near-infrared imager and slitless spectrograph, specializes in detecting faint objects near bright stars. Together, these instruments form humanity's most sophisticated tool for studying the atmospheres of distant worlds. When we talk about finding a second Earth, we need to be clear about what that means. We're not looking for an identical copy of our planet. Such a world might not even exist. Instead, scientists search for rocky planets in the habitable zone of their stars, regions where temperatures could allow liquid water to exist on the surface. Water is essential for life as we know it, so worlds with liquid water oceans become primary targets. But having water is not enough. A planet needs an atmosphere to maintain that water and regulate its temperature. It needs to orbit a stable star that does not bombard it with deadly radiation. It needs geological activity to recycle nutrients and maintain chemical balance. And it needs time, billions of years, for life to emerge and evolve. These requirements narrow the field considerably. Most exoplanets we have found are nothing like Earth. Giant gas worlds larger than Jupiter orbit closer to their stars than Mercury orbits our Sun. These hot Jupiters, as astronomers call them, experience temperatures that vaporize metal. Other worlds are super-Earths, rocky planets larger than Earth but smaller than Neptune, in a size range we do not see in our solar system. Many planets orbit red dwarf stars, small dim stars that make up 70% of all stars in the galaxy. These red dwarfs live for trillions of years, far longer than our Sun will last, but they tend to be volatile in their youth, erupting with flares that could strip away planetary atmospheres. Finding a truly habitable world requires threading a needle through countless obstacles. JWST has observed dozens of exoplanets since it began science operations in July 2022. Each observation adds to our understanding of how planets form, how their atmospheres evolve, and what conditions might support life. The telescope has found water vapor, carbon dioxide, methane, and even hints of more complex molecules that could indicate biological activity. Some of these discoveries have generated enormous excitement, with headlines proclaiming potential signs of life. Other discoveries have puzzled scientists, revealing atmospheric compositions that do not match any theoretical predictions. Each new world teaches us that planets are far more diverse and strange than we ever imagined. Before JWST, our ability to study exoplanet atmospheres was limited. The Hubble Space Telescope could detect water vapor and a few other molecules, but its observations lacked detail and precision. Ground-based telescopes faced interference from Earth's own atmosphere. JWST changed everything. Its infrared sensitivity and enormous light-collecting power allow it to study exoplanet atmospheres in unprecedented detail. The telescope can observe multiple transits of a planet as it passes in front of its star, building up data that reveals the atmospheric composition with remarkable accuracy. This capability has opened a new era in astronomy, one where we can actually characterize the air on alien worlds. The journey to this moment began long ago. In 1995, Swiss astronomers Michel Mayor and Didier Queloz discovered the first confirmed exoplanet orbiting a Sun-like star. They detected the planet, called 51 Pegasi b, by measuring the subtle wobble it caused in its star's motion. This wobble method, called radial velocity, became one of the primary techniques for finding exoplanets. In 2009, NASA launched the Kepler Space Telescope, which revolutionized exoplanet discovery by watching for the tiny dimming of starlight that occurs when a planet passes in front of its star. This transit method allowed Kepler to discover thousands of planets, including many in the habitable zones of their stars. But Kepler could only detect planets. It could not study their atmospheres. That required something more powerful. JWST's mission includes 4 main science goals. First, to observe the first galaxies that formed after the Big Bang. Second, to study how galaxies evolve over time. Third, to understand how stars and planetary systems form. And fourth, to study exoplanets and the origins of life. This last goal captures public imagination most intensely. The possibility of finding life beyond Earth drives much of the excitement around JWST's observations. Every time the telescope points at a potentially habitable world, humanity holds its breath, hoping this might be the moment we find evidence we're not alone. But finding that evidence is extraordinarily difficult. Life on Earth has transformed our planet's atmosphere in ways that are detectable from space. Oxygen makes up 21% of our air, a consequence of billions of years of photosynthesis by plants and microorganisms. Methane, another biosignature gas, is constantly replenished by biological activity. Without life, these gases would react and disappear. Their persistent presence in Earth's atmosphere is a clear sign something is producing them. If we could study Earth from light years away, as we study exoplanets, these biosignatures would jump out immediately. But on other worlds, things are more complicated. Gases that indicate life on Earth might be produced by non-biological processes elsewhere. A methane detection could mean microbes, or it could mean volcanic activity. Water vapor could indicate oceans teeming with life, or it could simply mean the planet formed with lots of water ice. Determining which is which requires careful analysis and multiple observations. This is where JWST excels. The telescope can study exoplanet atmospheres during transit, when the planet passes between its star and Earth. As starlight passes through the planet's atmosphere, molecules in that atmosphere absorb specific wavelengths of light. By analysing which wavelengths are missing, scientists can determine what molecules are present. This technique, called transmission spectroscopy, has become the primary method for characterising exoplanet atmospheres. JWST's spectrographs are so sensitive they can detect the chemical fingerprints of molecules at concentrations as low as parts per million. This precision allows researchers to build detailed pictures of atmospheric composition, temperature, and even weather patterns on distant worlds. The first results from JWST's exoplanet observations came in August 2022, when the telescope studied WASP 96b, a hot gas giant about 150 light-years away. The observation revealed water vapour, evidence of haze, and clear signatures of clouds in the planet's atmosphere. This was not a habitable world, far from it, but the observation demonstrated JWST's capability to characterise exoplanet atmospheres in extraordinary detail. The data showed features that previous telescopes could only hint at. Scientists realised they now had a tool capable of detecting not just the presence of molecules, but their abundances, their vertical distribution in the atmosphere, and how they interact with stellar radiation. Since then, JWST has observed dozens of exoplanets, building a diverse catalogue of atmospheric compositions. The telescope has studied everything from hot Jupiters to super-Earths to Neptune-sized worlds. Each observation reveals new surprises. Some planets have atmospheres dominated by hydrogen and helium, the lightest elements. Others show heavy atmospheres rich in heavier molecules like water, carbon dioxide, and methane. A few worlds appear to have lost their atmospheres entirely, stripped away by intense stellar radiation. The diversity is staggering and challenges many of our assumptions about how planets form and evolve. But among all these worlds, a few stand out as particularly intriguing in the search for a second Earth. These are the planets that orbit in the habitable zones of their stars that show signs of atmospheres and that might just possibly harbour the conditions necessary for life. They are not Earth twins, not by any stretch, but they represent our best current candidates for worlds where life could exist. JWST has turned its gaze towards several of these promising targets, and what it has found is both exciting and humbling. Understanding what makes a planet habitable requires understanding the delicate balance of conditions that allow liquid water to exist. Water is the universal solvent, the medium in which the chemistry of life unfolds. Every organism on Earth, from bacteria to blue whales, depends on liquid water. Scientists assume that life elsewhere will also require water, though we cannot rule out the possibility of life based on entirely different chemistry. For now, we follow the water, and that means focusing on planets in the habitable zone. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where a planet receives just the right amount of starlight to maintain liquid water on its surface. Too close to the star, and water boils away. Too far, and it freezes solid. The exact boundaries of the habitable zone depend on the star's temperature and brightness. Hot, luminous stars have habitable zones farther out. Cool, dim stars have habitable zones much closer in. Our Sun's habitable zone extends from about 0.95 astronomical units, just inside Earth's orbit, to about 1.37 astronomical units, just beyond Mars. Venus orbits too close and became a hellish greenhouse world. Mars orbits near the outer edge, and lost most of its atmosphere billions of years ago. But the habitable zone is not a guarantee of habitability. Venus sits near the inner edge of our Sun's habitable zone, yet its surface temperature is hot enough to melt lead. A runaway greenhouse effect trapped solar radiation and turned the planet into an oven. Mars, on the other hand, lost its atmosphere because its small size meant it could not generate a strong enough magnetic field to protect against the solar wind. These cautionary tales show that location alone does not ensure habitability. A planet needs the right size, the right atmosphere, the right geological activity, and probably a magnetic field. Even with all these factors aligned, life might not arise, or it might arise and go extinct before achieving complexity. The universe is not obligated to make life easy. Red dwarf stars present particular challenges for habitability. These stars are smaller and cooler than our Sun, which means their habitable zones are much closer in. A planet in the habitable zone of a red dwarf might orbit its star every few days or weeks, compared to Earth's one-year orbit. This proximity creates problems. Red dwarfs are prone to violent flares, especially when they are young. These flares could strip away planetary atmospheres before life has a chance to develop. Additionally, planets so close to their stars become tidally locked, meaning one side always faces the star and one side always faces away, just as the moon always shows the same face to Earth. This creates a permanent day side and a permanent night side, with extreme temperature differences between them. Tidally locked planets might still be habitable if they have thick atmospheres that can transport heat from the day side to the night side. The day side might be a scorching desert, while the night side is frozen wasteland. But a twilight zone between them could have moderate temperatures where liquid water persists. This twilight habitability is one of several scenarios scientists consider when evaluating red dwarf planets. Another possibility is the subsolar ocean model, where the day side has a warm ocean surrounded by ice on the cooler parts of the planet. This eyeball planet configuration could provide a stable habitat despite the extreme conditions on either side. Detecting atmospheres on exoplanets is the first step in assessing habitability. An atmosphere serves multiple critical functions. It regulates surface temperature through the greenhouse effect. It shields the surface from harmful radiation. It enables weather and climate patterns that distribute heat and water. It provides pressure that keeps water in liquid form. Without an atmosphere, a planet in the habitable zone is just a lifeless rock. JWST's ability to detect and characterize atmospheres makes it an essential tool in the search for habitable worlds. The telescope identifies atmospheric molecules by their absorption lines. Each molecule absorbs light at specific wavelengths, creating a unique spectral fingerprint. Water vapor absorbs strongly in the near-infrared at wavelengths around 1.4 and 1.9 micrometers. Carbon dioxide has absorption features at 4.3 and 15 micrometers. Methane absorbs at multiple wavelengths including 3.3 and 7.7 micrometers. Oxygen and ozone, the biosignatures Earth provides in abundance, are harder to detect but have features in the visible and infrared. By measuring how much light is absorbed at each wavelength during a planetary transit, JWST can determine which molecules are present and in what quantities. Biosignatures are molecules or combinations of molecules that indicate biological activity. On Earth, oxygen produced by photosynthesis and methane produced by microbes are the clearest biosignatures. But detecting these molecules on an exoplanet is not proof of life. Oxygen can be produced through photodissociation of water vapor by ultraviolet light. Methane can come from volcanic activity or comets. The key is finding combinations of molecules that are difficult to explain through non-biological processes. Oxygen and methane together, for example, would be a strong biosignature because these gases react with each other and should not coexist in large quantities unless something is continuously producing them. Another promising biosignature is dimethyl sulfide, a molecule produced on Earth primarily by marine phytoplankton. On our planet, dimethyl sulfide is only made by living organisms. Finding it on an exoplanet would be compelling evidence for life. This is why the possible detection of dimethyl sulfide on K2-18b generated such excitement. However, as we will explore in detail later, that detection remains controversial and unconfirmed. The lesson is that extraordinary claims require extraordinary evidence, and a single observation is never enough to conclude that life exists elsewhere. Temperature is another critical factor for habitability. Even a planet in the habitable zone can be too hot or too cold depending on its atmosphere. A thick atmosphere rich in greenhouse gases like carbon dioxide can trap heat and raise surface temperatures well above what the planet's distance from its star would suggest. Venus demonstrates this effect dramatically. Conversely, a planet with little atmosphere cannot retain heat effectively and might be frozen even in the habitable zone. Mars exemplifies this problem. The ideal scenario is an atmosphere similar to Earth's, with enough greenhouse gases to maintain comfortable temperatures, but not so much that a runaway greenhouse effect takes over. Atmospheric pressure matters too. Water can exist in liquid form only within a certain range of temperatures and pressures. At low pressures, water either freezes or evaporates depending on temperature, never forming stable liquids. Mars's thin atmosphere has such low pressure that liquid water cannot exist on the surface for more than brief moments. A habitable planet needs enough atmospheric pressure to keep water liquid across a range of temperatures. Earth's atmospheric pressure at sea level is about 1 bar. Some habitable worlds might have higher pressures, some lower, but there are limits. Too much pressure creates crushing conditions incompatible with life as we know it. Too little pressure and water evaporates or freezes. Clouds and hazes also affect habitability. Clouds reflect sunlight, cooling the planet. They also trap heat like greenhouse gases. The balance between these effects determines whether clouds stabilize or destabilize a planet's climate. On Earth, clouds play a complex role in climate regulation, sometimes warming the planet, sometimes cooling it. On exoplanets, the presence and nature of clouds can make the difference between a habitable world and an inhospitable one. JWST can detect clouds and hazes in exoplanet atmospheres, adding another layer of detail to our understanding of these distant worlds. The search for habitability extends beyond just finding liquid water. Life might require plate tectonics to recycle nutrients and maintain atmospheric composition over geological timescales. It might require a magnetic field to protect against stellar radiation and preserve the atmosphere. It might require a large moon to stabilize the planet's axial tilt and prevent wild climate swings. Earth has all these features, and they have contributed to its long-term habitability. Whether they are absolute requirements or just helpful accessories remains unknown. Life might be more adaptable than we imagine, capable of surviving in environments we would consider marginal or even hostile. This brings us to the tantalizing worlds JWST has been studying. Among thousands of known exoplanets, a few dozen orbit in habitable zones. Of those, a handful are rocky, or potentially rocky, and might have atmospheres. These are the prime targets, the worlds that could plausibly host life. JWST has already observed several of these planets, and the results are reshaping our understanding of what habitable worlds might look like. Some have defied expectations. Others have disappointed hopes. All have taught us that the universe is far stranger and more diverse than we anticipated. 40 light-years from Earth, in the constellation Aquarius, lies a star called TRAPPIST-1. It is small, cool, and dim, only slightly larger than Jupiter, and with less than 9% of our Sun's mass. If you stood on a planet in the TRAPPIST-1 system, the star would glow a deep red, casting everything in a crimson light. The star's dim output means its habitable zone is extremely close, much closer than Mercury orbits our Sun, and in that narrow band of space something extraordinary exists. 7 planets orbit TRAPPIST-1, all roughly Earth-sized, 3 of them squarely in the habitable zone. This makes TRAPPIST-1 the most promising planetary system ever discovered for finding life beyond Earth. The discovery of the TRAPPIST-1 planets sent shockwaves through astronomy. Astronomers found the first 3 planets in 2016 using the TRAPPIST South Telescope in Chile, a small facility designed to search for transiting planets around nearby dwarf stars. Follow-up observations with NASA's Spitzer Space Telescope revealed 4 additional planets, bringing the total to 7. The announcement in February 2017 made headlines worldwide. Here was a system packed with Earth-sized worlds, and multiple planets orbited in the habitable zone. If life arose on one of these planets, it might have spread to the others through asteroid impacts ejecting material between worlds. The possibility of an entire system teeming with life captured imaginations everywhere. All 7 TRAPPIST-1 planets orbit extremely close to their star. The innermost planet, TRAPPIST-1b, completes an orbit in just 1.5 days. The outermost TRAPPIST-1h takes about 19 days. For comparison, Mercury takes 88 days to orbit our Sun. These short orbital periods mean the planets move rapidly across the face of their star, transiting frequently and providing numerous opportunities for study. The planets are so close to each other that from the surface of one, you would see the others as disks larger than our Moon appears from Earth. They would not be points of light but actual worlds hanging in the sky, clearly showing surface features through a telescope. The 3 planets in the habitable zone are designated E, F, and G. TRAPPIST-1e orbits at a distance that receives about the same amount of light as Earth receives from the Sun. Its radius is 0.92 times Earth's radius, and its mass is 0.69 times Earth's mass, making it slightly smaller and less massive than our planet. If any world in the system has conditions suitable for life, TRAPPIST-1e is the leading candidate. TRAPPIST-1f and G orbit farther out, receiving less starlight. They might be cooler, possibly ice-covered, but could still have subsurface oceans kept liquid by tidal heating or geothermal activity. But there is a problem. Red dwarf stars like TRAPPIST-1 are highly active, especially when young. They emit powerful flares that could strip planetary atmospheres through a process called atmospheric erosion. High-energy radiation and stellar winds tear atoms from the upper atmosphere and carry them away into space. Over billions of years, this process could remove an entire atmosphere, leaving behind bare rock. Venus lost most of its water this way early in solar system history. Mars lost most of its atmosphere because it lacked a strong magnetic field to deflect the solar wind. The TRAPPIST-1 planets face similar threats. JWST has been observing the TRAPPIST-1 system intensively to determine whether these planets have atmospheres. The telescope began studying the system in 2022, and the results have been both illuminating and disappointing. Observations of TRAPPIST-1b, the innermost planet, found no evidence of a significant atmosphere. The planet appears to be bare rock, its atmosphere stripped away by the intense radiation so close to the star. This was not unexpected. TRAPPIST-1b orbits in a region too hot for liquid water, and its lack of atmosphere confirms it is uninhabitable. The real test came with TRAPPIST-1me, the most promising world. JWST observed the planet multiple times using its NIRISS and NIRSpec instruments. The observations measured how much starlight the planet blocked at different wavelengths during transit. If the planet had a thick atmosphere, that atmosphere would absorb light at specific wavelengths corresponding to water vapor, carbon dioxide, methane, and other molecules. The results were ambiguous. Some analyses suggested possible signs of a carbon dioxide atmosphere. Others found no clear evidence of any atmosphere at all. The data were consistent with a bare rock scenario, but they did not definitively rule out a thin atmosphere. A September 2025 study, analysing 4 transits of TRAPPIST-1e, concluded that the planet likely does not have a thick hydrogen-rich atmosphere, nor does it show strong evidence for a Venus-like or Mars-like atmosphere. However, the observations could not definitively determine whether the planet has a thinner Earth-like atmosphere or no atmosphere at all. The researchers emphasise that more observations are needed to answer the question conclusively. This uncertainty is frustrating, but reflects the difficulty of characterising small rocky planets around red dwarfs. The stellar activity creates noise in the data that can mask faint atmospheric signals. The problem stems from the star itself. TRAPPIST-1, like many red dwarfs, has star spots similar to sunspots but covering larger fractions of its surface. These spots are cooler and darker than the surrounding photosphere. When a planet transits, it might pass in front of a star spot, creating an anomaly in the light curve that mimics an atmospheric feature. Disentangling true atmospheric signals from these stellar contamination effects requires extremely careful analysis and multiple observations. JWST is capable of making these observations, but the process takes time. Each transit observation requires hours of telescope time, and each planet needs multiple transits to build up sufficient data. Despite these challenges, the TRAPPIST-1 system remains a high-priority target. The star's proximity at 40 light-years makes it one of the easiest red dwarf systems to study in detail. The multiple transiting planets provide numerous opportunities for comparative planetology, studying how planets in the same system evolve differently depending on their orbital positions. If one or more of these planets do have atmospheres, they will provide invaluable data about how rocky planets maintain their atmospheres around active red dwarfs. If they do not have atmospheres, that result is also important, showing the limits of habitability around small stars. TRAPPIST-1f and G, the other habitable zone planets, have also been targets for JWST observations, though results remain preliminary. These planets receive less stellar radiation than TRAPPIST-1e, which might help them retain atmospheres. However, they might also be too cold, with any water frozen solid. The ideal scenario would be a planet with a thick atmosphere that traps enough heat to maintain liquid water, despite the low stellar irradiation. Such a world would teach us that habitability is possible under conditions quite different from Earth's. The architecture of the TRAPPIST-1 system is remarkable. All 7 planets orbit in near resonance, meaning their orbital periods are related by small integer ratios. This resonance indicates the planets formed farther from the star and migrated inward together, maintaining their orbital relationships. The migration probably occurred early in the system's history, when the protoplanetary disk still existed. This history has implications for the planet's compositions. If they formed farther out, they might have incorporated more water ice and volatile compounds than if they had formed in place. Some models suggest the TRAPPIST-1 planets could be up to 50% water by mass, making them ocean worlds beneath thick ice shells or even global water oceans if their atmospheres provide enough greenhouse warming. The size and mass of the TRAPPIST-1 planets have been measured with remarkable precision, using both transit observations and radial velocity measurements. The planets are less dense than Earth, which supports the idea that they contain significant water. TRAPPIST-1e, for example, has a density consistent with a rocky core surrounded by a water layer perhaps hundreds of kilometers deep. This water might be liquid if the planet has an atmosphere, or frozen if it does not. The question of whether TRAPPIST-1e is an ocean world or an ice ball depends entirely on whether it has retained an atmosphere, and JWST has not yet definitively answered that question. From the surface of TRAPPIST-1e, the star would appear nearly 3 times larger in the sky than the Sun appears from Earth. It would glow deep red, bathing the landscape in crimson light. Because the planet is tidally locked, the star would remain fixed in the sky on the day side and forever below the horizon on the night side. The twilight zone between day and night would be the most habitable region, with moderate temperatures and a perpetual sunset sky. If the planet has an ocean, it might be concentrated on the day side, forming a warm sea surrounded by ice. The night side would be frozen solid, with any atmosphere condensing out as snow and ice. This creates a one-ocean world, strange and alien, but perhaps habitable. The search for atmospheres on TRAPPIST-1 planets continues. JWST has planned additional observations over the next several years. Each new observation adds data, refines measurements, and brings us closer to understanding whether these worlds are habitable. The telescope is also studying the star itself, measuring its activity and properties to better model how stellar radiation affects the planets. This comprehensive approach will eventually tell us whether life could survive on any TRAPPIST-1 planet, or whether the system is a graveyard of bare rocks stripped of their atmospheres long ago. Other red dwarf systems are also under study. Proxima Centauri, the closest star to our solar system at just 4 light-years away, has at least 2 planets, one of which orbits in the habitable zone. LHS 1140, another nearby red dwarf, hosts a particularly intriguing super-Earth that has become one of JWST's most exciting targets. These systems provide a diverse sample of red dwarf planets, allowing scientists to test theories about habitability around small stars. Red dwarfs are the most common stars in the galaxy, making up about 70% of all stars. If planets around red dwarfs can be habitable, then the galaxy might be full of habitable worlds. If red dwarf planets cannot retain atmospheres, then habitable planets might be far rarer than we hoped. The TRAPPIST-1 system represents both the promise and the challenge of finding a second Earth. The planets are Earth-sized, orbit in the habitable zone, and are close enough for detailed study. But they orbit a red dwarf star that might have destroyed their atmospheres. The jury is still out. JWST is collecting the data we need to render a verdict, but patience is required. Science does not happen overnight, and the search for habitable worlds demands careful, methodical work. The reward, however, could be extraordinary. If TRAPPIST-1e has an atmosphere, if it has oceans, if conditions that could support life, then we have found one of the most important worlds in the history of astronomy. And we would only be 40 light-years away from it. 48 light-years from Earth, in the constellation Cetus the Whale, orbits a planet that might be covered in ice with a single vast ocean on its day side, looking from space like a giant eyeball staring into the cosmos. Scientists call it LHS 1140b, and recent observations by the James Webb Space Telescope suggest this super-Earth might be the most promising potentially habitable world we have yet discovered. The planet is not an Earth twin. It is larger, more massive, and orbits a red dwarf star very different from our Sun. But it might have something Earth has that no other confirmed exoplanet possesses: liquid water on its surface. LHS 1140b was discovered in 2017 by the MERTH project, a network of small telescopes designed to search for transiting planets around nearby red dwarfs. The planet orbits its star every 24.7 days at a distance of just 0.09 astronomical units. 9 times closer than Earth orbits the Sun. This proximity would be scorching around a Sun-like star, but LHS 1140 is small and cool, with only 20% of our Sun's mass and 22% of its radius. The star is a red dwarf of spectral type M4.5v, glowing dimly in the infrared. Despite orbiting so close, LHS 1140b receives only 43% of the stellar flux Earth receives from the Sun, placing it near the outer edge of its star's habitable zone. When astronomers first characterized LHS 1140b, they faced a puzzle. The planet has a radius about 1.73 times Earth's radius, and a mass about 5.6 times Earth's mass. This makes it a super-Earth, larger and more massive than our planet but smaller than Neptune. The intriguing part is its density. the planet is less dense than it would be if made purely of rock and iron like Earth. Two scenarios could explain the low density. Either the planet has a thick hydrogen and helium atmosphere like a mini Neptune, or it contains substantial amounts of water. The question was crucial because a hydrogen-rich atmosphere would make the planet uninhabitable, while a water-rich composition could mean oceans. For years, LHS 1140b remained enigmatic. Multiple telescopes observed it, including Hubble, Spitzer, and TESS, but none could definitively determine whether it was a mini Neptune or a water world. The breakthrough came in December 2023 when JWST observed the planet using its NIRISS instrument. The observations captured the spectrum of starlight filtering through the planet's atmosphere during transit. When scientists analysed the data, they found something unexpected. The spectrum showed no signs of a hydrogen-rich atmosphere. The molecules they detected indicated the atmosphere was made of heavier elements, possibly nitrogen, carbon dioxide, and water vapour. This discovery was enormous. If LHS 1140b lacks a hydrogen atmosphere, then its low density must be due to water. Calculations suggest water could make up 10 to 20% of the planet's total mass. For comparison, water makes up only 0.02% of Earth's mass. LHS 1140b is not just a water world, it is a world where water dominates. If that water is liquid, and if the planet has an atmosphere to maintain moderate temperatures, then it could have oceans deeper than any on Earth. The tentative detection of nitrogen in the atmosphere made the discovery even more exciting. Nitrogen is the primary component of Earth's atmosphere, making up 78% of the air we breathe. On Earth, nitrogen provides atmospheric pressure and dilutes oxygen to levels that allow fire without everything constantly burning. If LHS 1140b has a nitrogen atmosphere, it would be the first exoplanet found with an Earth-like atmosphere, rather than the hydrogen-dominated atmospheres typical of gas giants or the carbon dioxide atmospheres of Venus and Mars. But the nitrogen detection remains uncertain. The signal is subtle, at the edge of what JWST can detect. Scientists emphasize that more observations are needed to confirm the atmosphere's composition. The research team has proposed additional observations focusing on detecting carbon dioxide, which should be easier to see if the atmosphere is substantial. Carbon dioxide has strong absorption features that JWST can measure precisely. Finding carbon dioxide would confirm the atmosphere is secondary, meaning it formed through volcanic outgassing or other processes after the planet's initial formation, rather than being leftover hydrogen from the protoplanetary disk. Assuming LHS 1140b has a nitrogen atmosphere and substantial water content, what would the planet look like? The planet is tidally locked, with one side always facing its star and one side always facing away. On the day side, the star would hang motionless in the sky, glowing a dull red. Temperatures there might be warm enough for liquid water, perhaps even reaching a temperate 20 to 30 degrees Celsius if the atmosphere provides greenhouse warming. The night side would be perpetually dark and frozen, with any atmosphere potentially condensing out as nitrogen, snow and ice. Between the two extremes lies a twilight zone, a ring around the planet where the sun sits on the horizon. This terminator region experiences perpetual dawn or dusk, with dimmer light than Earth's day but more than a moonlit night. If the planet has water, it might concentrate in a vast ocean on the day side surrounded by ice as temperatures drop toward the terminator and night side. This configuration creates the eyeball planet scenario, with a circular ocean representing the eyeball and ice covering the rest of the planet like a white sclera. Climate models suggest this eyeball configuration could be stable over geological time. The atmosphere would transport some heat from the day side to the night side through winds, but not enough to thaw the ice completely. The ocean would remain confined to the warmest region directly beneath the star. The ocean might be relatively small, perhaps 4,000 kilometers across, about the size of the Mediterranean Sea but likely much deeper. The ice sheets could be hundreds of meters thick, transitioning gradually from solid ice on the night side to slush and open water on the day side. Another possibility is that LHS 1140b is completely ice-covered, like Jupiter's moon Europa or Saturn's moon Enceladus. In this scenario, the planet's surface is a global ice shell perhaps 10 kilometers thick, with a liquid water ocean beneath. The ice would insulate the ocean from space, maintaining liquid water through geothermal heat from the planet's interior. This subsurface ocean world would still be potentially habitable, though life there would exist in eternal darkness, sustained by chemical energy rather than sunlight. The choice between surface ocean and subsurface ocean depends on the atmosphere's thickness and composition. A thick atmosphere with greenhouse gases could keep the surface warm enough for liquid water. A thinner atmosphere would allow the surface to freeze over. JWST's future observations will help distinguish between these scenarios by measuring how heat is distributed across the planet. If the night side is extremely cold with no atmospheric heat transfer, the surface is probably frozen over. If temperatures are more moderate across both hemispheres, a surface ocean becomes more likely. LHS 1140b's star is significantly less active than TRAPPIST-1. Red dwarfs come in different levels of volatility, and LHS 1140 appears to be a relatively calm star with fewer flares and less ultraviolet radiation. This quiescence is crucial for habitability. A calm star is less likely to strip away planetary atmospheres and less likely to bombard the surface with sterilizing radiation. Life on LHS 1140b, if it exists, would face fewer catastrophic events than life around more active red dwarfs. The star's age, estimated at several billion years, also means the planet has had time for life to arise and evolve if conditions permit. The planet's larger mass compared to Earth has both advantages and disadvantages for habitability. Higher gravity, about 1.8 times Earth's gravity, would make everything feel heavier. Humans visiting LHS 1140b would weigh almost twice what they do on Earth. This higher gravity might constrain the size and mobility of any organisms that evolve there, favouring compact, sturdy body plans. However, higher gravity also helps retain atmospheric gases. The stronger gravitational pull makes it harder for atmospheric molecules to escape into space, increasing the chances the planet has maintained its atmosphere over billions of years. The composition of LHS 1140b's ocean, if it exists, remains speculative. Earth's oceans contain dissolved salts, minerals, and organic compounds that make them suitable habitats for life. LHS 1140b's ocean might be freshwater, saltwater, or something entirely different depending on the planet's geological history. If the planet formed farther from its star and migrated inward, as many planets do, its water might have come from comets and asteroids that delivered volatile compounds along with water ice. This process could have seeded the ocean with organic molecules that provided the raw materials for life. Photosynthesis on LHS 1140b would work differently than on Earth. The red dwarf star's light is heavily weighted toward the red and infrared, with little blue or ultraviolet light. Any photosynthetic organisms would need to adapt to this spectrum, perhaps using pigments that absorb red light efficiently. Plants on LHS 1140b might appear black, absorbing light across the entire visible spectrum to gather enough energy. Alternatively, organisms might rely on chemosynthesis, deriving energy from chemical reactions rather than sunlight, as many deep-sea organisms do on Earth. Scientists regard LHS 1140b as one of the best targets for finding extraterrestrial life. The planet transits its star, making atmospheric studies possible. It orbits a relatively quiet star, reducing contamination effects in the data. It is nearby at just 48 light-years, allowing for detailed observations with current technology. And the initial JWST data suggest it has an atmosphere and abundant water. These factors combine to make LHS 1140b a prime candidate for future observations aimed at detecting biosignatures. The path forward requires more JWST observations. Researchers have proposed observing at least 15 more transits of LHS 1140b over the next 2 years. These observations will confirm whether nitrogen is present, detect carbon dioxide if it exists, and search for other atmospheric components like water vapor and methane. They will also measure how the atmosphere behaves at different wavelengths, revealing information about temperature, pressure, and cloud cover. With enough data, scientists will be able to construct a detailed model of the planet's climate and habitability potential. If LHS 1140b proves to have a substantial nitrogen atmosphere, temperate surface temperatures, and liquid water, it will become the first confirmed potentially habitable ocean world beyond our solar system. This would not prove life exists there, but it would show that planets with conditions suitable for life are real, and that we can detect them with our current instruments. It would mark a turning point in the search for life beyond Earth, transforming the question from whether habitable worlds exist to how common they are and whether they actually host life. The eyeball planet hangs in space 48 light-years away, waiting for us to uncover its secrets. JWST has pointed that direction, collecting photons that left the planet's atmosphere years ago. Those photons carry information about water, nitrogen, temperature, and weather. They might even carry hints of life, though detecting such signals will require years of observations and careful analysis. But for now, LHS 1140b stands as humanity's best hope for finding a second Earth, a world where oceans might exist beneath an alien sky. 124 light-years from Earth, in the constellation Leo, orbits an exoplanet that has become one of the most controversial worlds ever discovered. K2-18b is neither a hot Jupiter nor a rocky super-Earth. It is something in between, a sub-Neptune with a mass 8.6 times Earth's and a radius 2.6 times Earth's. The planet orbits in the habitable zone of its red dwarf star, receiving about the same amount of light as Earth receives from the Sun. For several years, K2-18b has tantalized scientists with hints that it might be a Hycean world, a hypothetical class of planet with a thick hydrogen atmosphere above a deep liquid water ocean. And in 2025, researchers announced they had detected possible signs of biosignature molecules in the planet's atmosphere. The scientific community responded with both excitement and deep skepticism. K2-18b was discovered in 2015 by NASA's Kepler Space Telescope during its K2 mission. The planet transits its star every 33 days, making it observable with multiple telescopes. Initial observations confirmed it is in the habitable zone, sparking interest in characterizing its atmosphere. In 2019, researchers using the Hubble Space Telescope announced they had detected water vapor in the planet's atmosphere, the first such detection for a habitable zone exoplanet. The discovery made headlines worldwide, though scientists cautioned that water vapor alone does not make a planet habitable. The concept of Hycean planets is relatively new in planetary science. These hypothetical worlds combine features of water worlds and hydrogen-rich mini-Neptunes. A Hycean planet has a thick atmosphere dominated by hydrogen gas, inherited from the protoplanetary disk during formation. Beneath this atmosphere lies a deep ocean of liquid water, potentially hundreds of kilometers deep. The hydrogen atmosphere provides tremendous greenhouse warming, keeping the water liquid despite the planet's distance from its star. Proponents of the Hycean planet idea argue these worlds could be habitable and might be more common than Earth-like planets. K2-18b fits the profile for a Hycean world. Its size and mass suggest a composition that is neither purely rocky nor purely gaseous. The planet's density implies significant amounts of water. Its thick atmosphere, confirmed by Hubble and later by JWST observations, contains hydrogen, water vapor, and carbon dioxide. The planet receives enough stellar radiation to maintain moderate temperatures. If the hydrogen atmosphere is not too thick and if liquid water exists beneath it, then conditions might support life, though life very different from what we know on Earth. In 2023, researchers led by Niku Madhusudan at the University of Cambridge used JWST's NIRISS and NEARSPEC instruments to observe K2-18b. The observations revealed methane and carbon dioxide in the atmosphere, along with hints of something far more intriguing, dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by marine phytoplankton, microscopic algae that live in the ocean. It is considered a strong biosignature because no known non-biological process on Earth produces significant amounts of DMS. The suggestion that DMS might exist in K2-18b's atmosphere sent ripples through the astrobiology community. Could this be the first indirect detection of life beyond Earth? The researchers emphasized caution. The DMS signal was weak, barely above the noise level in the data. It appeared as a subtle dip in the spectrum at wavelengths where DMS absorbs light. The team calculated that if DMS is present, its concentration might be thousands of times higher than on Earth, which itself was puzzling. Why would an alien world produce so much more DMS than Earth's oceans do? And could some unknown non-biological process create DMS on a Hycean world? The researchers acknowledged these uncertainties but argued the detection was intriguing enough to warrant follow-up observations. In April 2025, the same team published a new paper based on observations from JWST's MIRI instrument, which operates at longer wavelengths than NIRISS and NEARSPEC. The MIRI data showed possible detections of both dimethyl sulfide and dimethyl disulfide, another sulfur-containing molecule potentially produced by life. The researchers calculated the presence of these molecules to a statistical significance of about 3 sigma, meaning there is roughly a 1 in 370 chance the detections are random noise. This level of confidence is not enough to claim a definitive discovery. In particle physics, 5 sigma is typically required for a discovery claim, corresponding to odds of less than 1 in 3.5 million. The DMS detection on K2-18b falls well short of that threshold. Almost immediately, other scientists expressed skepticism. Jake Taylor of the University of Oxford reanalyzed the publicly available JWST data using standard techniques for exoplanet spectroscopy. His analysis found no strong evidence for DMS. The features the Cambridge team interpreted as DMS could also be explained by methane or instrumental artifacts. Taylor's work highlighted a fundamental problem. Spectral features from different molecules can overlap, especially when observing through the complex, multi-layered atmosphere of a planet. Distinguishing between molecules requires careful modelling and consideration of alternative explanations. Eddie Schwieterman, an astrobiologist at the University of California, Riverside, raised another concern. On Earth, when DMS is exposed to ultraviolet light from the sun, it breaks apart and forms other molecules like ethane and ethylene. These secondary products should also appear in the atmosphere if DMS is present. The Cambridge team's papers did not report detections of these molecules, which is puzzling. Why would DMS exist in K2-18b's atmosphere without the breakdown products you would expect? One possibility is that K2-18b's red dwarf star emits less ultraviolet light than our Sun, reducing the breakdown rate. Another possibility is that the DMS is not there at all, and the signal is caused by something else. The controversy underscores the challenges of detecting biosignatures on exoplanets. JWST is an incredibly powerful instrument, but it is not magic. The telescope collects photons that have passed through an exoplanet's atmosphere, travelled across light years of space, and entered the telescope's detectors. The signals are faint, often just a few % changes in brightness at specific wavelengths. Background noise, instrumental artifacts, and contamination from the host star can all introduce false signals. Extracting real atmospheric features from this data requires sophisticated statistical analysis and careful consideration of systematic errors. The debate also highlights how easy it is for media coverage to outpace scientific consensus. Headlines proclaiming the strongest evidence yet for extraterrestrial life generated enormous public interest. Many articles presented the DMS detection as if it were confirmed, downplaying the uncertainties and the need for independent verification. This pattern repeats frequently in exoplanet science. A tentative detection gets announced, generates headlines, and later turns out to be inconclusive or wrong after additional scrutiny. This cycle can erode public trust in science, making people skeptical of future announcements even when they are well supported. Despite the controversy, K2-18b remains an important target. The planet is real, it is in the habitable zone, and it has an atmosphere that JWST can study. Even if DMS is not present, understanding K2-18b's atmospheric composition teaches us about a class of planets we do not have in our solar system. Sub-Neptunes like K2-18b are extremely common in the galaxy, perhaps more common than either rocky planets or gas giants. Learning how they form, what they are made of, and whether they can be habitable is crucial for understanding planetary systems beyond our own. One major question about Hycean planets is whether they can actually harbour life. A thick hydrogen atmosphere would create enormous atmospheric pressure at the ocean surface, perhaps hundreds of times Earth's atmospheric pressure. Life would need to adapt to these crushing conditions. Additionally, hydrogen atmospheres are not stable over geological time. Hydrogen, being the lightest element, escapes to space relatively easily. Over billions of years, a Hycean planet might lose its hydrogen atmosphere, transitioning to something different. Whether life could arise and survive through such changes is unknown. The temperature profile of a Hycean atmosphere is also uncertain. The top of the atmosphere, where stellar radiation is absorbed, might be quite hot. The deep atmosphere near the ocean surface might be much cooler. This temperature gradient drives powerful winds and weather systems. Conditions at the ocean surface might be habitable, but the hostile conditions higher in the atmosphere could pose challenges for any aerial organisms or processes that require exposure to starlight, like photosynthesis. Another complication is the composition of the ocean itself. If the ocean is pure water, it might not have the dissolved minerals and nutrients that life requires. Earth's oceans are salty, rich in sodium, chlorine, sulfur, calcium, and trace elements, essential for biochemistry. A Hyxian world's ocean might be fresh water, or it might contain different dissolved substances depending on the planet's geological history. The chemistry of the ocean determines what kinds of biochemistry are possible. K2-18b will be observed again by JWST in the coming years. Additional data will either strengthen the case for DMS or rule it out entirely. If DMS is confirmed, it will trigger intensive follow-up observations searching for other biosignatures and trying to rule out non-biological explanations. If DMS is ruled out, K2-18b will still be valuable as a laboratory for studying sub-Neptune atmospheres, clouds, and chemistry. Either way, the planet has already taught us an important lesson. Finding biosignatures on exoplanets is far harder than it sounds, and extraordinary claims require extraordinary evidence. The controversy surrounding K2-18b also reflects deeper questions about how we search for life. Should we focus on planets most like Earth, rocky worlds with thin atmospheres in the habitable zones of sun-like stars, or should we cast a wider net, considering exotic possibilities like Hyxian worlds, ice-covered ocean moons, or even planets around stars very different from our Sun? Life might be more adaptable than we imagine, capable of arising and thriving in environments we would consider marginal. But resources are limited, telescope time is precious, and we must choose our targets carefully. Balancing caution with open-mindedness is one of the great challenges in astrobiology. For now, K2-18b remains a question mark. It is not a second Earth. It is not even particularly Earth-like, but it might be habitable in ways we're only beginning to understand, and it might just possibly host life, though we are very far from proving that. The planet reminds us that the universe is full of surprises, and that finding life beyond Earth may require looking in unexpected places. Whether K2-18b ultimately proves to be a living world, or just another lifeless planet, it has already earned its place in the history of astronomy as a world that made us think hard about what habitability really means. 280 light-years from Earth orbits a planet that should not have an atmosphere. TWI 561b is a super-Earth 1.4 times Earth's radius, and roughly twice Earth's mass, orbiting so close to its Sun-like star that it completes one orbit in less than 11 hours. The planet's surface is molten rock, a global magma ocean with temperatures reaching 3,700 degrees Fahrenheit on the day side. Conventional wisdom says planets this close to their stars cannot retain atmospheres. Intense stellar radiation and the heat from the molten surface should drive off any gases, leaving bare rock. Yet in December 2024, JWST found the strongest evidence yet that TOI 561b has a thick atmosphere above its magma ocean. This discovery is rewriting our understanding of how rocky planets evolve. TOI 561b belongs to a rare class called ultra-short-period exoplanets, worlds that orbit their stars in less than one day. These planets face extreme conditions. Tidally locked to their stars, they have a permanent day side constantly bombarded with stellar radiation and a cooler night side facing away. The day side receives so much energy that rock melts, forming vast lava oceans that churn and flow. Scientists have discovered dozens of ultra-short-period planets, but determining whether they have atmospheres has been challenging because these planets orbit Sun-like stars, which are relatively quiet compared to red dwarfs, but still present observational difficulties. JWST observed TOI 561b in May 2024, watching the planet as it passed in front of and then behind its star. When the planet transits, starlight filters through any atmosphere, revealing the atmosphere's composition. When the planet passes behind the star, called a secondary eclipse, the telescope measures the planet's own thermal emission. By combining transit and eclipse observations, researchers can determine both what molecules are in the atmosphere and how heat is distributed across the planet's surface. The observations revealed something startling. The planet's night side is much warmer than it should be if there were no atmosphere. Without an atmosphere, heat would not transfer efficiently from the day side to the night side. the night side would be nearly frozen solid, with temperatures dropping toward the boiling point of nitrogen. But TOI 561b's night side maintains a temperature of about 2,500 degrees Fahrenheit, hot enough to glow visibly. Something is transporting heat from the day side to the night side, and the most plausible explanation is a thick atmosphere generating powerful winds. The atmosphere's composition remains uncertain because the spectral features are subtle and difficult to interpret. The researchers modelled various atmospheric scenarios and found the data are best explained by a volatile rich atmosphere, meaning an atmosphere containing substantial amounts of molecules heavier than hydrogen and helium. The atmosphere might include water vapour, though at these temperatures water would be steam. It might contain carbon monoxide, carbon dioxide and silicate vapours from the evaporating magma. Clouds might form at high altitudes where temperatures drop enough for minerals to condense, creating exotic clouds of molten rock droplets or crystalline silicate particles. The atmosphere is not static. Powerful winds driven by the temperature difference between day and night side circulate gases around the planet. These winds might reach thousands of miles per hour, carrying heat from the scorching day side to the cooler night side. The wind patterns would be nothing like Earth's weather. Instead of trade winds and jet streams shaped by Earth's rotation and continents, TOI 561b would have a single dominant circulation pattern. Hot air rising on the day side, flowing toward the night side at high altitude, sinking as it cools, and returning to the day side at lower altitude. This circulation creates a heat transport mechanism that keeps the night side warmer than it would be otherwise. One of the most intriguing aspects of TOI 561b is its density. The planet is less dense than Earth, despite being larger and more massive. This lower density suggests the planet contains a significant fraction of lighter materials, possibly including water and other volatiles mixed with the rocky material. The presence of these volatiles is puzzling because planets this close to their stars should have formed at temperatures too high for water ice and other volatile compounds to condense. The leading explanation is that TOI 561b formed farther from its star, where temperatures were cooler, and migrated inward over time. During migration, the planet would have heated up, melting its surface and driving off some volatiles, but perhaps retaining enough to form an atmosphere. The magma ocean on TOI 561b's surface plays a crucial role in maintaining the atmosphere. As the planet's interior heats and convects, fresh magma rises to the surface, releasing dissolved gases through volcanic outgassing. On Earth, volcanic outgassing supplied much of our early atmosphere before plants began producing oxygen. On TOI 561b, the entire surface is volcanic, continuously replenishing atmospheric gases that might otherwise escape to space. This replenishment mechanism allows the planet to maintain its atmosphere despite the harsh conditions that would normally strip it away. The discovery challenges assumptions about planetary atmospheres. Scientists had thought planets this hot and this close to their stars could not keep atmospheres because the escape velocity, the speed needed to break free of the planet's gravity, would be too low relative to the thermal velocity of atmospheric molecules heated to such extreme temperatures. In simple terms, the molecules would be moving so fast they would fly off into space. But TOI 561b is more massive than Earth, which gives it stronger gravity and a higher escape velocity. This stronger gravity helps hold on to atmospheric gases even at extreme temperatures. The lesson is that planet mass matters crucially for atmospheric retention, perhaps more than temperature alone. TOI 560b is not habitable and never will be. Life as we know it cannot survive on a world with a molten surface and an atmosphere of steam and rock vapour, but the planet's atmosphere tells us something important about rocky planet evolution. If atmospheres can survive on ultra-hot worlds like TOI 561b, then atmospheres might be more resilient than we thought. Planets in habitable zones, which experience far less extreme conditions, might retain atmospheres more easily than models predicted. This increases the chances that habitable zone rocky planets around various types of stars have atmospheres and could potentially support life. The planet also provides a window into Earth's distant past. When Earth first formed 4.5 billion years ago, it was probably covered in a magma ocean, much like TOI 561b today. Asteroid and comet impacts kept the surface molten for millions of years. The early atmosphere would have been steam and carbon dioxide outgassed from the magma. Over time, as the surface cooled, water vapour condensed to form the first oceans. Studying a planet like TOI 561b helps us understand what conditions were like on early Earth and how planets transition from hostile molten worlds to cooler, more habitable ones. Another implication concerns the diversity of rocky planets. Before the discovery of exoplanets, our only examples of rocky planets were the 4 terrestrial planets in our solar system: Mercury, Venus, Earth, and Mars. We assumed rocky planets elsewhere would be similar, just different sizes and distances from their stars. But exoplanet discoveries have shattered that assumption. Rocky planets come in an astonishing variety. Some are covered in lava, others might be covered in ice. Some have thick atmospheres, others have none. Some orbit sun-like stars, others orbit red dwarfs or even the dead remnants of stars. The more we learn, the more we realize Earth is just one example of rocky planet among countless possible configurations. JWST's observation of TOI 561b represents a technical achievement as well as a scientific discovery. Detecting an atmosphere on a planet this hot required observing subtle differences in thermal emission at multiple wavelengths. The signal is only a few % change in brightness, easily lost in noise if the observations are not precise enough. JWST's large mirror and sensitive instruments make these observations possible. The telescope observed TOI 561b for more than 37 hours, following the planet through 4 complete orbits, accumulating enough data to confidently detect the atmospheric signal. This level of dedication and precision is what allows JWST to characterize exoplanet atmospheres in ways no previous telescope could achieve. The discovery of TOI 561b's atmosphere is still new and will undoubtedly inspire further research. Theorists will model the planet's atmosphere and magma ocean in more detail, trying to understand the circulation patterns, chemical equilibria, and long-term evolution. Observers will target other ultra-short period planets with JWST, determining whether TOI 561b is unique or representative of a larger population of lava worlds with atmospheres. Some researchers are already calling for follow-up observations of TOI 561b to measure its atmospheric composition more precisely, searching for specific molecules that would reveal the chemistry taking place in this extreme environment. Ultimately, TOI 561b reminds us that nature is more inventive than we are. Planets exist in configurations we never imagined, with atmospheres under conditions we thought impossible. Each discovery expands the boundaries of what we consider possible and forces us to revise our theories. The search for a second Earth is not just about finding an exact copy of our planet. It is about understanding the incredible diversity of worlds in the universe and learning which of those worlds might host life. TOI 561b will never harbour life, but it teaches us that atmospheres are more resilient than we thought, and that resilience increases the odds that habitable atmospheres exist elsewhere. Not all of JWST's exoplanet discoveries are about finding habitable worlds. Some are about encountering planets so bizarre, so unlike anything in our solar system, that they challenge our understanding of planetary physics. One such world orbits a pulsar, the rapidly spinning remnant of a dead star. The planet, catalogued as PSR J23-2654b, is being stretched into the shape of a lemon by its pulsar's intense gravity. Its atmosphere contains almost no oxygen or nitrogen, instead being dominated by helium and molecular carbon. Deep within this alien world, carbon clouds might condense into diamonds that rain down on whatever surface lies below. This is a planet that should not exist, orbiting a star that has already died, yet here it is, captured in extraordinary detail by JWST. Pulsars are neutron stars, the collapsed cores left behind when massive stars explode as supernovae. These objects are incredibly dense, packing more than the Sun's mass into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh billions of tons on Earth. Pulsars spin rapidly, sometimes completing hundreds of rotations per second, and emit beams of electromagnetic radiation from their magnetic poles. As the pulsar rotates, these beams sweep across space like a lighthouse beam, appearing as regular pulses when detected from Earth. Hence, the name pulsar. Finding planets around pulsars is unusual but not unprecedented. The first confirmed exoplanets ever discovered in 1992 orbited a pulsar called PSR B712-7+2. Those planets probably formed from the debris of the supernova explosion that created the pulsar, condensing from a disk of material around the newly formed neutron star. PSR J2326b might have a similar origin, or it might have existed before the supernova and somehow survived the cataclysm. Either way, the planet now endures extreme conditions unimaginable in our solar system. The planet orbits just 1 million miles from the pulsar, about 1/40th the distance between Mercury and the Sun. At this proximity, the pulsar's gravitational pull is immense. Tidal forces, the difference in gravitational pull between the near and far sides of the planet, distort the planet into an ellipsoid shape, elongated like a football or lemon. This tidal distortion is far more extreme than the tidal bulges Earth's oceans experience from the Moon. PSR J232650b is being continuously squeezed and stretched, generating internal heat from the friction of materials grinding against each other. This tidal heating probably keeps the planet's interior molten. JWST observed PSR J23222650b in 2024 using its ENEAR-SPEC instrument. Because there is no bright star to contaminate the observations, the telescope could study the planet's atmosphere directly without the usual difficulties of separating planetary light from starlight. The spectra revealed an atmosphere unlike any seen before. The dominant gases are helium and molecular carbon, specifically C2 and C3 molecules, which are chains of 2 and 3 carbon atoms bonded together. Molecular carbon is extremely rare in planetary atmospheres because carbon preferentially bonds with other elements like hydrogen, oxygen and nitrogen if those elements are available. The dominance of molecular carbon in PSR J23222650b's atmosphere means there is almost no hydrogen, oxygen or nitrogen present. This composition is bizarre. Most planetary atmospheres contain hydrogen or oxygen, or both. Earth's atmosphere is nitrogen and oxygen. Venus and Mars have carbon dioxide atmospheres. Gas giants like Jupiter have hydrogen and helium. But PSR J23222650b has molecular carbon and helium, a combination never seen before. Researchers are puzzling over how such an atmosphere could form and remain stable. One possibility is that the supernova that created the pulsar stripped away hydrogen and nitrogen, leaving behind heavier elements like carbon and helium. Another possibility is that intense radiation from the pulsar has photodissociated other molecules, breaking them apart and leaving molecular carbon as a residue. The planet's atmosphere likely contains clouds, but not water clouds or ammonia clouds like we see in our solar system. Instead, the clouds might be made of carbon particles, essentially soot. At high altitudes where temperatures are cooler, carbon might condense out of the gas phase and form tiny solid particles that scatter light. These carbon clouds would give the atmosphere a dark, sooty appearance. Deeper in the atmosphere, where pressure and temperature are higher, carbon particles might aggregate and grow, potentially forming graphite or even diamond. The concept of diamond rain, where solid carbon falls through the atmosphere as gemstones, sounds like science fiction, but is a real possibility on worlds with carbon-rich atmospheres and high pressures. The discovery of PSR J23222650b's unusual atmosphere demonstrates JWST's versatility. The telescope is not just a tool for finding habitable worlds, it is a laboratory for studying planetary physics under extreme conditions. By observing planets in environments vastly different from our solar system, scientists test their theories and discover new atmospheric chemistry they never imagined. Each strange world adds to the catalogue of planetary possibilities and expands our understanding of what planets can be. Another recent JWST discovery involved a hot Jupiter with twin gas tails streaming behind it, defying explanation. The planet orbiting close to its star is losing atmospheric mass at a prodigious rate. The escaping gases form two distinct tails pointing in different directions, driven by stellar winds and the planet's orbital motion. This observation reveals atmospheric escape in action, showing how planets can lose their atmospheres over time when exposed to intense stellar radiation. Studying atmospheric escape on hot Jupiters helps scientists understand the fate of planets in close orbits and informs models of atmospheric retention on smaller, rockier worlds. JWST has also observed superpuff planets, worlds with extremely low densities like cotton candy in space. These planets have masses similar to Neptune but radii much larger, giving them densities lower than Saturn's. Scientists are not sure how superpuff planets form or why they have such low densities. The planets might have enormous extended atmospheres made mostly of hydrogen and helium, or they might have large amounts of water and other volatiles that reduce their overall density. JWST's spectroscopic observations are helping to distinguish between these scenarios by measuring the atmospheric composition and determining what the planets are made of. The diversity of exoplanets discovered by JWST and other telescopes is both thrilling and sobering. Thrilling because each new type of planet teaches us something new about planetary formation and evolution. Sobering because it shows just how unusual Earth might be. Most exoplanets are nothing like Earth. They're either too big, too hot, too close to their stars, or orbiting the wrong kind of star. The more planets we find, the more we appreciate the specific circumstances that allowed Earth to become habitable. A stable sun-like star, a planet at the right distance, a large moon to stabilize the axial tilt, plate tectonics to recycle nutrients, a magnetic field to protect the atmosphere, and billions of years of stability for life to evolve. All these factors had to align for Earth to become what it is today. But the diversity also suggests that habitable worlds might exist in configurations we have not yet imagined. Life might arise on ice-covered ocean moons heated by tidal forces. It might exist in the atmospheres of gas giants, floating as aerial microbes in temperate cloud layers. It might cling to existence on rogue planets ejected from their star systems, surviving on geothermal heat alone. The universe is vast and inventive, and limiting our search to Earth-like planets around Sun-like stars might cause us to miss inhabited worlds that are nothing like Earth. JWST continues to survey the exoplanet population, observing everything from the smallest rocky planets to the largest gas giants. Each observation adds to the database, helping scientists understand the statistical distribution of planet types and their atmospheric properties. This statistical approach is crucial because we can only study a few planets in great detail. By observing many planets at moderate detail, we learn which types are common and which are rare, what atmospheric compositions are typical, and how planets correlate with their stars. This big picture understanding is essential for planning future missions and targeting the best worlds for deeper study. The exotic planets JWST has discovered remind us that the universe is full of surprises. We have barely scratched the surface of exoplanet diversity, with thousands of planets still waiting to be characterized and millions more waiting to be discovered. Each bizarre world, from lemon-shaped planets around pulsars to diamond rain worlds to super puffs to lava worlds with impossible atmospheres, teaches us that planets are more varied and fascinating than we ever imagined. And somewhere among this incredible menagerie, there might be worlds where life has found a way to survive and thrive despite conditions that seem impossible from our Earth-centric perspective. Understanding how JWST detects exoplanet atmospheres requires understanding some basic principles of spectroscopy and the ingenious techniques astronomers use to tease faint signals out of noisy data. When a planet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere before reaching us. This light carries imprints of the molecules in that atmosphere, creating dark lines in the spectrum where specific wavelengths have been absorbed. By measuring these absorption lines with extreme precision, JWST can determine what molecules are present and in what quantities. This technique, called transmission spectroscopy, is the primary method for characterizing exoplanet atmospheres. The process begins with the planet's orbit. For transmission spectroscopy to work, the planet must transit its star as seen from Earth. This geometric requirement means we can only study a fraction of all exoplanets, those whose orbital planes happen to align with our line of sight. For a planet orbiting a Sun-like star at Earth's distance, the probability of transit is about 0.5%. For planets orbiting closer to their stars, the probability increases because the planet subtends a larger angle, as seen from distant vantage points. This is why hot Jupiters and close-orbiting super-Earths are overrepresented in studies of exoplanet atmospheres. They are more likely to transit, and their transits are easier to detect. When a transit occurs, the planet blocks a small fraction of the star's light. For an Earth-sized planet transiting a Sun-like star, the dimming is about 0.1%, 1 part in 10,000. JWST can measure such tiny changes because its detectors are extraordinarily sensitive, and because astronomers observe many photons, millions or billions, allowing statistical analysis to pull the signal out of the noise. The depth of the transit, How much the star dims depends on the planet's size. Larger planets block more light, creating deeper transits, but the transit depth is not uniform across all wavelengths. If the planet has an atmosphere, that atmosphere absorbs light at specific wavelengths corresponding to the molecules it contains. At those wavelengths, the planet appears slightly larger because the atmosphere extends above the solid surface. This makes the transits slightly deeper. By measuring the transit depth at many wavelengths and comparing them, astronomers create a transmission spectrum showing how much light is absorbed at each wavelength. Peaks in the spectrum indicate molecules present in the atmosphere. JWST's spectrographs split starlight into its component wavelengths with incredible precision. NIR-SPEC, the near-infrared spectrograph, covers wavelengths from 0.6 to 5.3 micrometers, the near-infrared range where many important molecules have absorption features. MIRI, the mid-infrared instrument, extends coverage to longer wavelengths from 5 to 28 micrometers, detecting molecules that absorb in the mid-infrared. NIRIS, the near-infrared imager and slitless spectrograph, specializes in wide-field spectroscopy, observing multiple objects simultaneously without needing a slit to isolate individual targets. Each instrument uses diffraction gratings or prisms to spread light into a spectrum. The light falls onto detectors that measure the intensity at each wavelength with high precision. JWST's detectors are cooled to extremely low temperatures, near absolute zero, to reduce thermal noise that would otherwise swamp the faint signals from exoplanets. The telescope's sunshield, a 5-layer structure the size of a tennis court, keeps the instruments cold by blocking sunlight and heat from Earth and the Moon. This passive cooling system allows JWST to detect infrared light that would be invisible to a warm telescope. Observing a transiting exoplanet with JWST requires careful planning. The telescope must be pointed at the star well before the transit begins, establishing a baseline of the star's brightness. As the planet transits, the telescope records the dimming at multiple wavelengths. After the transit, observations continue to establish a post-transit baseline. The entire observation might last several hours, and for some planets, JWST observes multiple transits to accumulate more data and improve signal-to-noise ratio. The data processing pipeline is complex. Raw images from the detectors undergo calibration to correct for instrumental effects like detector nonlinearity, flat fielding, and cosmic ray hits. The spectra are extracted from the images, separating the target star's light from background light. Wavelength calibration ensures each pixel in the spectrum corresponds to a known wavelength. Finally, the transit light curve is created showing how brightness changes with time at each wavelength. Atmospheric models are then fitted to the transmission spectrum. These models calculate what spectrum you would expect for various atmospheric compositions, temperatures, and pressure profiles. Researchers run thousands or millions of model simulations, varying parameters like water vapor abundance, methane concentration, cloud cover, and temperature structure. They compare each model to the observed spectrum and calculate how well it fits. The best-fitting models reveal the most likely atmospheric properties. Degeneracies complicate this process. Different atmospheric compositions can produce similar spectra, especially at the modest signal-to-noise ratios achievable with current technology. Clouds and hazes can obscure molecular features, making atmospheres appear featureless even if molecules are present. High-altitude clouds effectively shrink the atmosphere's detectability, muting all spectral features. Distinguishing between a truly featureless atmosphere and one obscured by clouds requires observations at multiple wavelengths where clouds behave differently. Secondary eclipse observations complement transmission spectroscopy. When the planet passes behind the star, its own thermal emission is blocked, causing a tiny dimming. By subtracting the star-only signal from the combined star plus planet signal, astronomers isolate the planet's emission. This thermal emission spectrum reveals the temperature and composition of the planet's day side. Unlike transmission spectroscopy, which probes the atmosphere's edge, emission spectroscopy samples the deeper atmosphere where most of the mass resides. Direct imaging is another technique JWST employs for some planets. Planets far from their stars can be resolved as separate points of light, rather than being lost in the star's glare. JWST uses coronagraphs, devices that block the star's light, revealing faint companions. Direct imaging allows spectroscopy of the entire planet, not just the thin atmospheric shell probed during transit. However, direct imaging only works for planets far enough from their stars and bright enough in infrared light to be detectable above the residual starlight. This limits the technique to young, hot giant planets orbiting relatively nearby stars. JWST's instruments also employ clever tactics to minimize systematic errors. The telescope often uses a technique called stare mode, where it points at a single target without moving, reducing pointing errors and jitter. It uses bright reference stars to monitor and correct for telescope drifts. It observes targets at multiple orientations, rotating the telescope to spread systematic errors across different detector pixels and making them easier to identify and remove. Stellar contamination is a persistent challenge. Stars have spots like sunspots on our Sun that are cooler and darker than the surrounding photosphere. If a transiting planet crosses a star spot, the transit depth changes because the planet is blocking a darker region of the star. This creates false signals that can mimic atmospheric features. Similarly, stellar flares and brightness variations due to rotation or pulsation introduce noise. For red dwarf stars, which are highly active, stellar contamination can be severe enough to obscure atmospheric signals entirely. Correcting for these effects requires modelling the star itself, using multiple transit observations to average out variations, or observing reference stars with similar properties to the target star. The statistical significance of detections matters enormously. In science, a detection is typically considered reliable if it reaches 5 sigma significance, meaning the probability of it being random noise is less than 1 in 3.5 million. Many exoplanet atmospheric detections do not reach this level. They might be 3 sigma, corresponding to odds of 1 in 370, or even lower. Such detections are considered tentative and require follow-up confirmation. Media coverage often presents tentative detections as definitive discoveries, creating confusion and setting unrealistic expectations. Understanding the statistical rigor behind scientific claims is crucial for interpreting exoplanet discoveries accurately. JWST's sensitivity is limited by fundamental factors. Photon noise. The random arrival of photons sets a lower limit on the signal-to-noise ratio achievable in a given observation time. Zodiacal light, sunlight scattered by dust in the solar system, adds background noise. The star's intrinsic brightness determines how many photons the telescope collects. Fainter stars provide fewer photons, requiring longer observations to achieve the same signal-to-noise ratio. Very distant planets, hundreds or thousands of light-years away, are generally too faint for detailed atmospheric characterization with current technology. Future observations will push these limits. By observing the same planets repeatedly, astronomers can average multiple transits, improving signal-to-noise and detecting fainter features. By coordinating JWST observations with ground-based telescopes and other space missions, researchers can cover wider wavelength ranges and validate detections independently. And by refining data analysis techniques, scientists will squeeze more information out of existing data, teasing out subtle signals that current methods miss. The technology enabling JWST's exoplanet studies represents decades of development. The telescope's mirrors are made of beryllium, a lightweight metal that maintains its shape at cryogenic temperatures. The mirrors are coated with gold, which reflects infrared light efficiently. The sunshield uses layers of kapton, a tough plastic film, stretched on a frame and separated by gaps that block heat radiation. The detectors are mercury-cadmium telluride arrays for the near-infrared instruments, and arsenic-doped silicon detectors for MIRI, chosen for their sensitivity and low noise at infrared wavelengths. Ground support includes the Space Telescope Science Institute in Baltimore, which schedules observations and distributes data to researchers worldwide. Data analysis pipelines developed by large teams of scientists and programmers process the raw data and make it accessible for scientific analysis. The archive of JWST data is publicly available, allowing any scientist to download and analyze observations. This open data policy accelerates discovery and ensures independent verification of results. JWST's mission is planned for at least 10 years, possibly extending longer if the telescope remains healthy. During this time, it will observe hundreds of exoplanets, building a comprehensive picture of atmospheric diversity. Each observation adds to humanity's knowledge, bringing us closer to answering the ultimate question: are we alone? The technology that makes this possible is the culmination of centuries of astronomical progress, from Galileo's first telescope to Hubble's deep space observations to JWST's infrared vision. We are fortunate to live in an era when finding and characterizing worlds around distant stars has become not just possible, but routine. The search for a second Earth is no longer science fiction. It is science fact, happening now as JWST collects photons from alien worlds light years away. The search for a second Earth is a marathon, not a sprint. JWST has been observing exoplanets for just over 2 years as of late 2024, and already it has revolutionized the field. But the telescope's work is far from finished. Hundreds of observations are planned over the coming years, targeting the most promising habitable zone planets with the goal of detecting biosignatures or ruling them out definitively. Each observation builds on previous ones, accumulating data that allows ever more precise characterization of atmospheric properties. The pace is deliberate and methodical because the stakes are so high. Claiming to have found evidence of life beyond Earth is not something to be done lightly. Several factors will determine whether JWST can find a true second Earth. First, habitable worlds must exist within reach of the telescope's sensitivity. If the nearest habitable planet is hundreds or thousands of light years away, JWST may not be able to collect enough light to detect biosignatures. Second, those habitable planets must have atmospheres with detectable biosignature gases. If life on alien worlds produces different chemical signatures than Earth life, we might miss them. Third, the planets must transit their stars as seen from our vantage point. Non-transiting planets cannot be studied with transmission spectroscopy, limiting the sample to a fraction of all potentially habitable worlds. Current candidates for detailed study include LHS 1140b, TRAPPIST-1e, and a few dozen other planets in habitable zones around nearby stars. JWST has begun observing many of these targets and will continue over the next several years. Each planet requires dozens of hours of observations to characterize its atmosphere thoroughly. Balancing the need for deep observations of a few key targets against surveying a broader sample of planets presents a difficult trade-off. Focusing on 1 or 2 planets provides the highest quality data, but risks missing habitable worlds elsewhere. Surveying many planets provides a statistical view of habitability, but spreads telescope time thinly, limiting the detail available for any single planet. The development of future telescopes and missions will complement JWST's work. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will have a field of view 100 times larger than JWST, allowing it to survey thousands of exoplanets and identify the best targets for follow-up observations. The Habitable Worlds Observatory, currently in early planning stages, is envisioned as a successor to JWST specifically designed to find and characterize habitable planets. This telescope would be optimized for detecting biosignatures like oxygen and methane in the atmospheres of Earth-sized planets around Sun-like stars. Launch is not expected until the late 2030s or 2040s, meaning JWST will remain our premier tool for exoplanet atmospheres for at least another decade. Ground-based telescopes are also advancing. The extremely large telescope under construction in Chile will have a mirror 39 meters across, 6 times the diameter of the largest current telescopes. Its adaptive optics systems will correct for atmospheric turbulence, providing images nearly as sharp as space-based telescopes. The ELT will be able to directly image some exoplanets and characterize their atmospheres using spectroscopy. Other giant telescopes, like the 30-meter telescope and the Giant Magellan Telescope, will provide complementary capabilities. Together, these observatories will form a powerful network for studying exoplanets from both space and the ground. Advances in data analysis techniques will also play a crucial role. Machine learning algorithms are being trained to identify spectral features in noisy data, potentially finding signals that traditional methods miss. Improved atmospheric models that account for clouds, hazes, and photochemistry more accurately will allow better interpretation of observations, and statistical methods for combining data from multiple observations and multiple instruments will increase confidence in detections, distinguishing real signals from instrumental artifacts. The timeline for finding a second Earth depends on luck as well as capability. If a nearby, transiting, habitable planet with a clear atmosphere exists and hosts life that produces biosignature gases, JWST might detect it within the next few years. If no such planet is within reach, we may need to wait for future missions with greater sensitivity and different capabilities. Patience and persistence are essential. The history of astronomy is full of long searches that eventually succeeded. Percival Lowell spent years searching for Planet X beyond Neptune, and though he never found it, his efforts eventually led to the discovery of Pluto. The search for exoplanets took decades before the first confirmed detections in the 1990s. The search for habitable worlds and life beyond Earth may take decades more. Public interest in the search for a second Earth is immense, and that interest drives funding and support for missions like JWST. When headlines announce possible biosignatures on distant planets, even tentative ones, people around the world pay attention. This public engagement is vital for maintaining political and financial support for astronomy. However, it also creates pressure to announce results prematurely or to oversell findings. Scientists must balance their enthusiasm with caution, presenting results honestly and acknowledging uncertainties. The media has a responsibility to report discoveries accurately, avoiding sensationalism and distinguishing between confirmed findings and speculative possibilities. Philosophical and ethical questions also arise as we get closer to finding habitable worlds and potentially life. If we detect biosignatures on a planet 40 light-years away, what does that mean for humanity? We cannot travel there with current technology. Even the fastest spacecraft would take hundreds of thousands of years. We cannot communicate in real time. A message would take 40 years to reach the planet and 40 more for a response. The knowledge that life exists elsewhere would transform our understanding of our place in the universe, but it would not lead to contact or exchange in the foreseeable future. How should we process such a discovery emotionally and culturally? Some researchers argue we should be preparing now for the possibility of detecting biosignatures in the next few years. This includes establishing protocols for confirming detections, coordinating follow-up observations by multiple telescopes, and communicating results to the public in a responsible way. The discovery of life beyond Earth would be one of the most important moments in human history, and we should not approach it haphazardly. Learned societies and international organisations have begun developing frameworks for how to respond to such a discovery, though much work remains to be done. The search for a second Earth also intersects with the search for life in our own solar system. Missions to Mars, Europa, Enceladus and Titan are looking for signs of past or present life. If life is found on any of these worlds, even if it is just microbes, that would profoundly change our estimates of how common life is in the universe. If life arose independently on two or more bodies in our solar system, it suggests life might be extremely common throughout the galaxy. If our solar system has only one living world, Earth, that suggests life might be rare. JWST's exoplanet discoveries will complement these solar system missions, providing a broader perspective on habitability and biology. A crucial question is what kinds of biosignatures JWST should look for. On Earth, oxygen and methane together form a compelling biosignature because these gases react with each other and should not coexist in large quantities unless constantly replenished. But alien life might produce different gases. Phosphine, detected controversially in Venus's atmosphere, is another potential biosignature. Dimethyl sulfide, as discussed earlier for K218b, could indicate marine life. Ammonia, nitrous oxide, and ethylene are also possibilities. JWST's spectrographs can detect many of these molecules if they are present in sufficient abundance. But knowing which molecules to prioritize in the search requires assumptions about biochemistry that might not hold on alien worlds. False positives are another concern. Non-biological processes can produce gases that look like biosignatures. Volcanism can release methane. Photochemistry driven by stellar ultraviolet light can produce oxygen through water vapor dissociation. Lightning in ammonia-rich atmospheres might create nitrogen oxides. Distinguishing between biological and non-biological sources requires understanding the planet's geology, atmospheric chemistry, and stellar environment. This holistic approach is essential but complicates the interpretation of observations. Collaboration between fields will be crucial for interpreting JWST's discoveries. Atmospheric scientists model how gases behave under different conditions. Geochemists study volcanic outgassing and mineral interactions. Astrobiologists explore what kinds of life might exist under different environmental conditions. Statisticians develop methods for assessing the significance of detections. engineers design instruments for future missions. All these disciplines contribute to the search for a second Earth, and success will require integrating knowledge across fields. The role of international cooperation cannot be overstated. JWST is a joint mission of NASA, the European Space Agency, and the Canadian Space Agency, with contributions from scientists and engineers worldwide. Future missions will likely be even more international, as the costs and technical challenges of building powerful space telescopes exceed what any single nation can shoulder alone. The search for life beyond Earth is a global endeavour, uniting people across borders and cultures in pursuit of a common goal. This spirit of cooperation is one of the most hopeful aspects of space exploration. As JWST continues its mission, each new observation brings us closer to answering whether we are alone. LHS 1140b might prove to have oceans and an atmosphere suitable for life. TRAPPIST-1e might surprise us with signs of habitability, or some other world, not yet identified as a top candidate, might turn out to be the one. The universe has a way of surprising us, and the search for a second Earth is full of unknowns. But one thing is certain: we are living through the beginning of an era when humanity can actually find and characterize worlds that might host life. That is extraordinary, and future generations will look back on this time as a turning point in our understanding of the cosmos. If you found this journey through the cosmos fascinating, hit that like button and subscribe. The search for life beyond Earth is just beginning, and you do not want to miss what comes next. The universe is full of wonders, and we are living in the golden age of their discovery. Reading the atmosphere of a planet orbiting another star light years away requires extracting signals so faint they border on impossible. When JWST observes an Earth-sized planet transiting a Sun-like star, the dimming caused by the planet-blocking starlight is roughly 1 part in 10,000. The atmospheric signal, the additional dimming caused by molecules in the atmosphere absorbing specific wavelengths, is about 1 part in 100,000 or smaller. This is like trying to detect the shadow of a mosquito crossing a searchlight beam from miles away. Yet JWST does this routinely, and understanding how requires diving into the physics of light, the chemistry of atmospheres, and the mathematics of signal processing. Light itself is the key. When electromagnetic radiation passes through a gas, molecules in that gas can absorb photons at specific energies corresponding to the molecular structure. Each type of molecule has a unique set of energy levels determined by how its atoms vibrate and rotate. Water molecules, for instance, vibrate in 3 primary modes: symmetric stretching, where both hydrogen atoms move away from the oxygen simultaneously; asymmetric stretching, where one hydrogen moves toward the oxygen while the other moves away; and bending, where the angle between the 2 hydrogen-oxygen bonds changes. Each vibrational mode absorbs light at a specific wavelength. Water's strongest absorption features in the infrared occur at 1.4, 1.9, 2.7, and 6.3 micrometers, corresponding to different combinations of these vibrational modes. Carbon dioxide has different vibrational modes because its structure is linear, with 1 carbon atom between 2 oxygen atoms. The symmetric stretch, where both oxygens move away from the carbon, does not absorb infrared light because the molecule's dipole moment does not change. But the asymmetric stretch and the bending mode do create changing dipoles, and therefore absorb light strongly at 4.3 and 15 micrometers. Methane, with its tetrahedral structure of 1 carbon surrounded by 4 hydrogens, has even more complex vibrational patterns, creating absorption features at 3.3, 7.7, and other wavelengths. When JWST observes a transiting planet, it measures how much starlight reaches its detectors at thousands of different wavelengths simultaneously. If the planet has no atmosphere, the amount of light blocked should be constant across all wavelengths, determined only by the planet's physical size. But if molecules are present in the atmosphere, they will absorb additional light at their characteristic wavelengths, creating dips in the transmission spectrum. The depth of these dips reveals how much of each molecule is present. Deeper dips mean higher concentrations. Shallow dips mean trace amounts. Temperature plays a crucial role in atmospheric spectroscopy. At higher temperatures, molecules have more kinetic energy and occupy higher vibrational and rotational states. This broadens the absorption features, spreading them across wider wavelength ranges. It also shifts the features slightly to different wavelengths. By analysing the precise shape of absorption features, scientists can determine not just what molecules are present, but also the temperature at which they exist. This allows construction of temperature-pressure profiles showing how atmospheric temperature changes with altitude. Pressure affects spectra through a process called pressure broadening. At high pressures, molecules are packed closely together and collide frequently. These collisions interrupt the absorption process, spreading the absorption features across wider wavelength ranges and reducing their peak strength. At low pressures, molecules are far apart, collisions are infrequent, and absorption features are narrow and sharp. By measuring how broad or narrow the features are, scientists can infer the atmospheric pressure where the absorption is occurring. Clouds and hazes complicate everything. If a planet has thick clouds high in its atmosphere, starlight cannot penetrate to the deeper layers where most molecules reside. The clouds effectively reduce the atmosphere's transparency, muting all spectral features. The spectrum becomes nearly flat, showing little variation with wavelength. This is frustrating because it prevents detailed characterization. Some of the most interesting planets, those that might have liquid water and complex chemistry, could have cloudy atmospheres that hide their secrets from our instruments. Distinguishing between a truly featureless atmosphere and one obscured by clouds requires observations at multiple wavelengths where cloud opacity varies. Clouds made of water droplets scatter shorter wavelengths more strongly than longer wavelengths, a phenomenon called Rayleigh scattering that also makes Earth's sky blue. By observing across a wide wavelength range from visible to infrared, scientists can model the cloud properties and in some cases see through gaps where clouds are less opaque. JWST's broad wavelength coverage, from 0.6 to 28 micrometers, helps tremendously in this regard. Hazes, consisting of tiny particles suspended in the atmosphere, create similar problems. On Titan, Saturn's largest moon, a thick hydrocarbon haze obscures the surface entirely at visible wavelengths. Only infrared and radar can penetrate the haze to reveal the landscape below. Exoplanets might have similar hazes made from photochemical reactions, where ultraviolet light from the star breaks apart molecules and the fragments recombine into complex hydrocarbons that condense into particles. Detecting hazes and characterizing their composition requires careful modeling of how particles scatter and absorb light at different wavelengths. Stellar activity introduces systematic errors that can mimic or obscure atmospheric features. Stars are not perfect spheres of uniform brightness. They have spots, like sunspots, that are cooler and darker than the surrounding photosphere. They have faculae, bright regions associated with magnetic activity. They have granulation, a mottled appearance caused by convection cells rising and falling in the star's outer layers. When a planet transits, it might pass in front of spots or faculae, changing the apparent transit depth in ways that have nothing to do with the planet's atmosphere. Red dwarf stars are particularly problematic. These stars often have spots covering 10 to 20% of their surface, compared to less than 1% for the Sun at solar maximum. The spots can be several hundred degrees cooler than the surrounding photosphere, creating strong spectral features. When a planet transits a spotted star, the observed spectrum is a complex mixture of light from the planet's atmosphere, light from the star's spotted surface, and light from the star's unspotted surface. Disentangling these contributions requires modelling the star itself and observing multiple transits to average out the variations. Correcting for stellar activity is an active area of research. One approach uses simultaneous observations at multiple wavelengths. Star spots affect all wavelengths similarly, while atmospheric features are wavelength specific. By comparing the transit depth at different wavelengths, researchers can identify and remove stellar contributions. Another approach observes the star when the planet is not transiting, measuring the star's natural brightness variations. This establishes a baseline that can be subtracted from transit observations. A third approach uses models of stellar surfaces, predicting how spots and faculae should affect observations and fitting these models to the data. The concept of scale height is fundamental to understanding transmission spectroscopy. Scale height is the vertical distance over which atmospheric pressure decreases by a factor of E about 2.718. It depends on temperature and gravity through the formula H, kTmg, where K is Boltzmann's constant, T is temperature, M is the mean molecular weight, and G is surface gravity. On Earth, The scale height is about 8 kilometers. On a hot Jupiter with temperatures of around 1500 Kelvin and lower gravity, the scale height might be hundreds of kilometers. Larger scale heights make atmospheres puffier and easier to detect because a greater vertical extent of atmosphere can be probed during transit. This is why hot Jupiters were the first exoplanets to have their atmospheres characterized. Their high temperatures and large sizes give them enormous scale heights, producing strong spectral features that early instruments could detect. Rocky planets like Earth have small scale heights, making their atmospheric signals much weaker. JWST's improved sensitivity finally makes it possible to detect these faint signals, but it remains challenging. An Earth-sized planet transiting a Sun-like star produces atmospheric signals only a few parts per million, requiring exceptional precision. The retrieval process, where atmospheric properties are extracted from observed spectra, employs sophisticated statistical methods. Researchers use Bayesian inference, a framework for updating probabilities based on data. They start with prior assumptions about what the atmosphere might contain, run thousands or millions of atmospheric models with different parameters, calculate what spectrum each model would produce, and compare those predictions to the observations. Models that match the data well have their probabilities increased. Models that match poorly have their probabilities decreased. After many iterations, the method converges on the most likely atmospheric composition and structure. Markov chain Monte Carlo is a common technique for exploring the vast parameter space of possible atmospheres. The algorithm randomly proposes changes to atmospheric parameters, calculates the resulting spectrum, and accepts or rejects the changes based on how well the new spectrum matches the observations. Over time, the algorithm samples the full range of possible atmospheres, building up a probability distribution for each parameter. Researchers can then report not just the best fit values, but also the uncertainties, showing which parameters are well constrained and which remain ambiguous. Degeneracies are a persistent challenge. Different combinations of atmospheric properties can produce similar spectra, especially when data quality is limited. High clouds and low water vapor abundance, for example, might produce the same muted spectrum. High metallicity and low temperature might mimic the effects of each other. Breaking these degeneracies requires observations at additional wavelengths, where the degenerate scenarios produce different signals, or combining transmission spectroscopy with emission spectroscopy to constrain temperature independently. The interpretation of biosignatures requires even more care. Detecting oxygen and methane together in an exoplanet atmosphere would be exciting, but does it prove life? On Earth, photosynthesis produces oxygen, and methanogenic bacteria produce methane, and their coexistence is a strong sign of biology. But on an exoplanet, perhaps oxygen comes from photodissociation of water vapor, and methane from volcanic outgassing. Distinguishing between biological and abiotic origins requires understanding the planet's geology, the star's ultraviolet output, atmospheric chemistry, and the timescales over which gases are produced and destroyed. One promising approach focuses on chemical disequilibrium. In a lifeless atmosphere, chemical reactions proceed until equilibrium is reached, where the rates of forward and reverse reactions balance. Life disturbs this equilibrium by continuously producing gases that would not otherwise coexist. On Earth, oxygen and methane are in extreme disequilibrium. They react to form carbon dioxide and water, and without life constantly producing them, they would disappear in thousands of years. Finding gases in disequilibrium on an exoplanet would suggest some process, possibly life, is maintaining the imbalance. But even disequilibrium is not foolproof. Volcanic outgassing can inject gases faster than chemistry can equilibrate them. Photochemistry driven by stellar radiation can create disequilibrium. Impact events delivering comets or asteroids can temporarily spike certain gas concentrations. Seasonal variations in climate can drive oscillations in atmospheric composition. Each of these processes must be ruled out before concluding that life is the best explanation for observed biosignatures. This is why scientists speak of biosignatures in probabilistic terms rather than definitive proof. A strong biosignature increases the probability that life is present but never proves it with certainty. A weak signal might be intriguing but is not compelling. The standard for claiming detection of extraterrestrial life will be extraordinarily high, likely requiring multiple independent biosignatures, observations over extended periods to rule out transient phenomena, and exhaustive modelling to eliminate abiotic explanations. JWST is providing the data to start this process, but confirming life will require patience and rigor. The development of laboratory experiments to calibrate atmospheric models is crucial. Researchers create gas mixtures in sealed chambers, expose them to ultraviolet light, and measure the resulting spectra. They simulate the pressures and temperatures of exoplanet atmospheres and observe how molecules behave. They study photochemistry, how light breaks apart molecules and creates new compounds. These lab experiments provide the fundamental data needed to interpret JWST's observations accurately. Without them, models would be based on theory alone, and uncertainties would be much larger. Ultimately, the science of detecting and characterizing exoplanet atmospheres is a blend of physics, chemistry, statistics, and instrumentation. It requires pushing technology to its limits, extracting signals from noise, and carefully considering alternative explanations for every observation. The fact that we can read the composition of atmospheres on worlds dozens or hundreds of light years away is a testament to human ingenuity and the power of the scientific method. Each spectrum JWST captures brings us closer to understanding the diversity of planetary atmospheres and perhaps to finding signs of life beyond Earth. One of the most powerful aspects of JWST's exoplanet observations is the ability to compare planets in ways never before possible. By studying multiple planets around the same star, or planets of similar sizes and masses around different stars, scientists can test theories of planetary formation and evolution. This field, called comparative planetology, has been practiced in our solar system for decades, but is now extending across light years to distant planetary systems. The insights are transforming our understanding of how planets work. Consider the TRAPPIST-1 system, with its 7 Earth-sized planets. All 7 formed from the same protoplanetary disk, all orbit the same star, yet they have evolved into different worlds depending on their distances from the star and their individual properties. TRAPPIST-1b, the innermost, is likely bare rock stripped of its atmosphere by intense radiation. TRAPPIST-1c and d may have thin atmospheres or none at all. TRAPPIST-1e sits in the habitable zone and might retain an atmosphere. TRAPPIST-1f and g receive less radiation and might be ice-covered ocean worlds. TRAPPIST-1h, the outermost, is cold and mysterious. By comparing these planets directly, scientists can isolate the effects of stellar radiation, tidal heating, and distance from the star. The density differences among the TRAPPIST-1 planets are revealing. The inner planets are denser, suggesting rocky compositions with less water. The outer planets are less dense, suggesting more water ice or volatile materials. This gradient matches what we see in our own solar system, where rocky terrestrial planets orbit close to the Sun and ice-rich bodies orbit farther out. The pattern reflects the temperature gradient in the protoplanetary disk. Close to the star, temperatures were too high for water ice and other volatiles to condense. Only rocky and metallic materials could solidify. Farther out, temperatures dropped enough for ices to form, and planets incorporated more of these lighter materials. Migration complicates this simple picture. Many planets do not form where we find them today. They form farther out and migrate inward due to gravitational interactions with the disk or with other planets. Hot Jupiters, giant planets orbiting extremely close to their stars, almost certainly migrated inward because temperatures close to the star would have been too high for giant planets to form in situ. The TRAPPIST-1 planets likely migrated as well, moving inward together while maintaining their orbital resonances. Evidence for migration comes from the resonances themselves, which are difficult to establish unless the planets move through the disk together. Comparing planets around different stars reveals the influence of stellar properties. Planets around Sun-like stars experience steady radiation with moderate ultraviolet output. Planets around red dwarfs face volatile stars with frequent flares and intense ultraviolet bursts when young. Planets around massive stars receive torrents of ultraviolet light that can photo-evaporate atmospheres within millions of years. By comparing how similar planets evolve around different types of stars, scientists can determine which stellar environments are most conducive to habitability. One intriguing comparison involves super-Earths and mini-Neptunes. These planets, intermediate in size between Earth and Neptune, do not exist in our solar system but are extremely common in the galaxy. Some super-Earths are rocky worlds with thin atmospheres or no atmospheres. Others are mini-Neptunes with thick hydrogen-helium envelopes. The dividing line between these two categories is not sharp, and understanding what determines whether a planet becomes a super-Earth or mini-Neptune is a major question. JWST observations are helping answer this question by measuring atmospheric compositions and searching for hydrogen-dominated atmospheres. If a planet has a hydrogen atmosphere, it is a mini-Neptune. If it lacks hydrogen and has a secondary atmosphere of heavier molecules, it is a super-Earth. The boundary seems to occur around 1.5 to 2 Earth radii, with smaller planets generally being rocky and larger planets generally being gas-rich. But there are exceptions, and understanding why requires comparing many planets. Atmospheric escape plays a key role. Planets that formed with hydrogen atmospheres can lose them over time if they orbit close enough to their stars. Intense ultraviolet radiation heats the upper atmosphere, giving gas molecules enough energy to escape the planet's gravity. This process, called photoevaporation, can strip away entire atmospheres in hundreds of millions of years. Planets that lose their primordial hydrogen atmospheres become super-Earths with exposed rocky surfaces. Planets that retain their atmospheres remain mini-Neptunes. The outcome depends on the planet's mass, its distance from the star, and the star's ultraviolet output. TOI 561b provides a case study in atmospheric retention under extreme conditions. Despite being an ultra-hot world with a molten surface, it has retained a thick atmosphere, possibly because its mass gives it strong enough gravity to hold onto gases even at high temperatures. Comparing TOI 561b to other ultra-short period planets will reveal whether atmospheric retention at such close distances is common or unusual. Another comparison involves atmospheric composition as a function of metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium. Stars with high metallicity have more heavy elements, which means the planets forming around them also have access to more heavy elements. This should affect planetary composition and atmospheric chemistry. Observations are beginning to show that planets around metal-rich stars tend to have atmospheres rich in carbon and oxygen compounds, while planets around metal-poor stars have simpler atmospheric chemistry. This makes sense because the raw materials available during planet formation determine what the planets are made of. Weather patterns on exoplanets provide another avenue for comparison. Hot Jupiters exhibit extreme weather, with winds reaching thousands of miles per hour and temperature differences of thousands of degrees between day and night sides. Some hot Jupiters show evidence of jet streams and large-scale circulation patterns similar to Earth's Hadley cells but vastly more intense. Tidally locked planets experience different weather than rotating planets because the permanent day-night division drives persistent circulation rather than the changing patterns we see on Earth. Clouds on exoplanets come in exotic varieties unknown in our solar system. Silicate clouds, made of vaporized rock that condenses at high altitudes, give some hot Jupiters a dark appearance. Sulfur dioxide clouds might exist on volcanic worlds. Water ice clouds form on cold planets. Iron clouds, where metallic iron vapor condenses into droplets, could exist on the hottest worlds. By comparing cloud properties across many planets, scientists are learning how clouds form under different conditions and how they affect planetary energy balance and observability. The presence or absence of moons is another factor in comparative planetology. In our solar system, large moons like Earth's moon and Jupiter's Galilean satellites play important roles in their planet's evolution. Earth's moon stabilizes our axial tilt, preventing wild climate swings. Jupiter's moons experience tidal heating that drives geological activity. Exomoons, if they exist, could have similar influences. Detecting exomoons is challenging because they are small and their signals are subtle, but JWST and future telescopes might find them around some giant exoplanets. Ring systems, like those around Saturn, might also exist around exoplanets. Rings form from disrupted moons or captured debris and can affect a planet's appearance and how it interacts with stellar radiation. Rings would create periodic variations in transit depth as they pass in front of the star at different angles. So far, no confirmed exoplanet ring systems have been found, but absence of evidence is not evidence of absence. Future observations with higher precision might reveal rings around some planets. Magnetic fields are crucial for planetary habitability, but difficult to detect on exoplanets. Earth's magnetic field protects our atmosphere from the solar wind and cosmic rays, preventing atmospheric erosion. Mars lacks a strong magnetic field and lost most of its atmosphere billions of years ago. Detecting magnetic fields on exoplanets requires observing their interaction with the stellar wind, which creates auroras and radio emission. JWST cannot detect these signals, but radio telescopes might, and combining optical, infrared and radio, observations could reveal which exoplanets have protective magnetic fields. Tidal heating is another process best understood through comparison. Jupiter's moon Io is the most volcanically active body in the solar system, due to tidal heating from Jupiter's gravity. Saturn's moon Enceladus has geysers erupting through its ice shell, powered by tidal energy. Some exoplanets in tight orbits experience similar tidal effects, keeping their interiors molten and driving geological activity. This activity can outgas atmospheres, generate magnetic fields through dynamo action, and create conditions for habitability even on planets far from their stars' habitable zones. By comparing planets across many systems, scientists are building a comprehensive theory of planetary physics that applies throughout the galaxy. This theory will guide the search for habitable worlds by identifying which planetary characteristics are most important for life. It will inform the design of future missions by highlighting the observations needed to distinguish between different types of planets, and it will ultimately tell us whether Earth is typical or exceptional, whether habitable worlds are common or rare, and whether life arises easily wherever conditions permit or requires unlikely circumstances to emerge. JWST is extraordinary, but it is not the end of the story. Even as it reveals new worlds and characterizes their atmospheres, scientists and engineers are designing the next generation of telescopes that will push even further into the cosmos. These future observatories will have capabilities JWST cannot match, allowing them to find and study planets JWST cannot reach. They will search for biosignatures on Earth-sized planets around Sun-like stars, directly image rocky planets in habitable zones, and probe the atmospheres of distant worlds in wavelengths JWST cannot access. The future of exoplanet science is bright, and the discoveries yet to come may dwarf what JWST has already achieved. The Nancy Grace Roman Space Telescope, named after NASA's first chief astronomer, is scheduled to launch in 2027. Roman will have a field of view 100 times larger than JWST, allowing it to survey vast areas of sky and discover thousands of new exoplanets. The telescope's primary mission includes studying dark energy and mapping the galaxy, but exoplanet science is a major component. Roman will use a technique called gravitational microlensing to find planets that do not transit their stars and cannot be detected by radial velocity. Microlensing occurs when a star passes in front of a more distant star, and the foreground star's gravity acts as a lens, magnifying the background star's light. If the foreground star has planets, they create additional brightening spikes in the light curve, revealing their presence. Microlensing is particularly good at finding planets far from their stars, including worlds in the outer regions of planetary systems where transit and radial velocity methods are ineffective. Roman will discover planets in orbits similar to Jupiter and Saturn, providing a census of giant planets in the galaxy. It will also find rogue planets, worlds ejected from their star systems and wandering through space alone. These rogue planets might outnumber planets orbiting stars, though they're nearly impossible to detect because they emit no light and are not illuminated by a nearby star. Roman's discoveries will complement JWST's detailed characterizations. While Roman finds planets, JWST can follow up on the most interesting ones, studying their atmospheres and searching for biosignatures. This tag-team approach maximizes the scientific return from both missions. Roman's wide surveys will also identify the best targets for the next flagship mission, the Habitable Worlds Observatory. The Habitable Worlds Observatory, or HWO, is in the early planning stages and is envisioned as a direct successor to JWST, specifically optimized for finding and characterizing habitable planets. The telescope would have a mirror 6 meters or larger, comparable to JWST but designed for ultraviolet, visible and near-infrared wavelengths rather than infrared alone. This wavelength coverage is crucial for detecting oxygen and ozone, which have strong features in the ultraviolet and visible. HWO would use a coronagraph or starshade to block light from the star, allowing direct imaging of planets orbiting close enough to be in habitable zones. A starshade is an enormous flower-shaped screen flown separately from the telescope, positioned tens of thousands of kilometers away to cast a shadow that blocks starlight before it reaches the telescope. The starshade's edges are carefully shaped to cancel diffraction, creating an extremely dark shadow at the telescope's location. This allows the telescope to see faint planets next to bright stars without the starlight overwhelming the planetary signal. Starshade technology is being tested now, and if successful, could revolutionize exoplanet imaging. HWO would be capable of taking actual images of Earth-sized planets in habitable zones around nearby sun-like stars, showing them as points of light separated from their stars. Spectroscopy of these planets would reveal atmospheric composition, searching for oxygen, water vapor, methane, and other biosignatures. HWO could observe dozens of potentially habitable worlds, building a comprehensive picture of how common life is in the galaxy. The mission is targeted for launch in the late 2030s or 2040s, pending funding and technology development. Ground-based telescopes are also advancing rapidly. The Extremely Large Telescope, or ELT, under construction by the European Southern Observatory in Chile, will have a primary mirror 39 meters in diameter, making it the largest optical telescope ever built. Its light-collecting power will dwarf current telescopes, and its adaptive optics system will correct for atmospheric turbulence, providing images nearly as sharp as space telescopes. The ELT will be able to directly image some exoplanets and characterize their atmospheres using spectroscopy. The 30-meter telescope and the Giant Magellan Telescope, both under construction, will have similar capabilities. These giant telescopes will work together with space-based observatories, providing complementary observations across different wavelengths and techniques. Ground-based telescopes have the advantage of being upgradable, with new instruments added over time as technology advances. Space telescopes like JWST are fixed at launch, with limited ability to upgrade. This complementarity ensures both approaches remain valuable. Another promising technology is interferometry, where multiple telescopes observe the same target simultaneously, and their light is combined to simulate a much larger telescope. The Very Large Telescope Interferometer in Chile already does this in the infrared, achieving angular resolution equivalent to a telescope over 100 meters across. Future interferometers, possibly in space, could achieve even better resolution, potentially imaging surface features on exoplanets rather than just seeing them as points of light. The search for technosignatures, signs of advanced civilizations, is also advancing. JWST can search for atmospheric pollution, industrial chemicals that would indicate technological activity. Chlorofluorocarbons, the same compounds that depleted Earth's ozone layer, could serve as technosignatures because they are not produced naturally, but are created by industrial processes. Finding CFCs in an exoplanet's atmosphere would suggest an industrial civilization. Other technosignatures include city lights on the night side of a planet, detectable as a faint glow, and megastructures like Dyson spheres that would absorb starlight and re-radiate it in the infrared. Radio telescopes continue searching for deliberate signals from extraterrestrial civilizations. The search for extraterrestrial intelligence, or a SETI, uses large radio telescopes to scan millions of stars for narrow-band signals that could only be artificial. So far, SETI has found no confirmed signals, but the search continues. Combining SETI with exoplanet discoveries allows targeted searches of planetary systems known to have habitable zone planets, increasing the chances of success. The timeline for these future missions depends on funding, technology development, and political will. HWO is not yet approved and faces competition for limited budgets. The giant ground-based telescopes are under construction, but have experienced delays and cost overruns. Roman is funded and on schedule for 2027, but science missions can be cancelled or delayed. Despite these uncertainties, the trajectory is clear. Telescopes are getting larger, more sensitive, and more sophisticated. Each generation reveals more about the universe than the last, and there is no reason to expect this trend to stop. Looking further ahead, concepts exist for truly enormous space telescopes with mirrors tens of meters across, assembled in space from multiple segments. Telescopes operating at wavelengths JWST cannot access, like the far infrared or the ultraviolet, could reveal phenomena invisible to current instruments. And telescopes positioned at more distant locations, like the solar gravitational focus point where the sun's gravity acts as a lens to magnify distant objects, could theoretically image exoplanets with extraordinary detail. possibly even resolving continents and oceans. The search for a second Earth is a long-term endeavour that will span decades or centuries. JWST is an early step, a reconnaissance mission identifying candidates and demonstrating that atmospheric characterization is possible. Roman will expand the sample, finding thousands of new worlds. HWO and the giant ground-based telescopes will focus on the best candidates, searching intensively for biosignatures. Future missions beyond these will refine our understanding, confirming or refuting tentative detections and exploring planets we have not yet discovered. Each generation of astronomers builds on the work of the previous generation. We are fortunate to live in an era when finding exoplanets has transitioned from impossible to routine, when characterizing their atmospheres has become feasible, and when the search for life beyond Earth has moved from speculation to science. The telescopes we are building now will serve astronomers for decades, and the discoveries they make will shape our understanding of the cosmos for generations. JWST is showing us what is possible. The future will show us what is real. If you have been captivated by this journey through the search for a second Earth, hit that like button and subscribe. The cosmos is full of wonders, and we're only beginning to uncover them. Stay curious, keep exploring, and remember that somewhere out there, orbiting a distant star, there might be a world where oceans glitter under an alien sun, where life has found a way, and where we might someday find evidence that we're not alone in the universe.